Okay, so quick look at these. I've just pulled up some problems from the 2.1 or 2.2 assignments. Stuff we talked about yesterday. So they want you to find the horizontal tangents. Okay, let's just, none of this is beyond, I mean, you know the calculus to do this. The tricks we talked about the other day are sufficient, but what you have to kind of interpret some of these too. What's that mean? Horizontal tangents. Sounds like kind of a weird deal right now, but we spend a heck of a lot of time in calculus talking about horizontal tangents. This is our first brief look at them. We'll do a lot of that later. What's a horizontal? I mean, it's exactly what it says. What's that mean then?
The minimum and maximum line.
Okay, okay. I guess I should say a tangent. When we say tangents, we mean tangent lines.
So the zero line with slope is zero?
Yeah, there you go. That's exactly it. Tangent lines where the slope is zero. So, for example, if this is my curve, then we're just looking for maybe the places like right there or right there where we have horizontal tangent lines. Okay, equal, which equation is it? Not that one.
Oh, okay.
Right, this one, if I set this one equal to zero, that's gonna give me the places where y is zero, so those would be the x-intercepts. Those might be useful to us for other reasons, but how are we gonna find where the tangent lines are horizontal?
No,
You already told me that's where the slope is zero.
We couldn't do that.
What do we know, now what's our calculus, when we're talking slope now, and we haven't spent a lot of time on this. Say it again? No? The derivative, that's it, the derivative, right? Remember that,
What have we been talking about for the past couple of days?
well, it's hard to, now I know where you are right now, you've been working on practicing the skills, and how we haven't been talking about a lot of, why are we doing this, or we haven't looked at it strategically and used this stuff in problems like this yet. I mean, you've just been working on how do I do derivatives, how do I get good at doing derivatives. But that's exactly what we do here, isn't it? Derivative is when we think of derivative in calculus, we're always thinking slope stuff, right? So derivative and slope are one and the same. So we're gonna set the derivative equal to zero and solve for x. And all those x values, the solutions of that equation are gonna be the x values where these horizontal tangents occur. If I wanted to find the points of tangency, let's just say hypothetically, let's just do this one. What's this derivative? This will be an easy one. Yeah, I could call it y prime, I could call it dy dx, I could call lots of things. But if this is the original function, what's the derivative? Using our new trick. Power rule.
F of x minus delta. Is that what you're
Well, yeah, but we have a trick now. We don't have to do any of that stuff. Right? No, you're right. That's what a derivative is in general. Derivative is the limit of f of x plus delta x minus f of x. But we got these tricks now, right? What's our rule? What's the derivative of x to the n? N x to the n minus 1. So then what's the derivative of x cubed?
3x squared.
Aha.
We wrote this down.
And
Minus 22x.
22x?
Yeah.
And
35. Plus 35.
and derivative of 9?
Plus 0.
0. Good. So that's it. Nice. So the derivatives, now if I want to find where we have horizontal tangents, I'll just set this derivative function equal to 0 and solve. Okay. Now we don't. Does that make sense? Okay. So I don't want to take the time to do. I mean, that's easy. That's just some algebra 2 stuff. Let's just say hypothetically, this probably. I mean, what are the odds this is right? But let's say hypothetically that one of our solutions was at x equals 3. If I want to find the point of tangency, how would I do that? Because I need two. Let's say this is the point we're looking for. I know the x coordinate. How would I find the y coordinate?
Plug it in.
Plug it into here?
No, the original.
Plug it into here. Good. Good. Okay, very good. Okay, now we're moving. This is good. All right. Okay, now what about this guy? This one looks terrible. And I'll tell you,
That looks atrocious.
pretty soon, we're going to have a way that, not that we would want to do it that way.
Extension 304.
Who?
Nick Levy.
Okay. Not that we would want, the best way to do this one right here is the way we're gonna do it now, the way we're gonna talk about doing it. But we will have a way here in the near future of just taking this as is and differentiating as a product and a quotient. But right now, we don't have any rules for those, right? We have shortcuts for just a very few things. For for powers, right? Power functions, and for sine and cosine. And, and that's really it. And a constant, yeah, but that's really just a power, isn't it? So, we don't have any big fancy derivative rules for quotients and products. What would we have to do before we could begin to differentiate this thing? What would we do? Well, it's already factored. In fact, that's kind of a problem for us. Because it's factored, it's a product of factors.
We gotta put it back together.
Ah, we need to say it again? Expand it, that's the right word. Yeah, we want to expand this out, right? We'd expand the top out and make this a cubic polynomial, right?
Yeah.
And then if I get a cubic polynomial on top, and once again, I'm not gonna take the time to do this. You guys can do that. But if I have a cubic polynomial on top divided by x cubed, what can I do with that?
Make it vertical.
Well, okay, the first term would be, but I could take each term and just divide it by x cubed, couldn't I?
Yeah.
And then each term is gonna end up being some power of x, positive or negative, doesn't matter, right? The power rule applies in both cases. We can take the derivative of a negative power of x and the power rule still applies, right? Okay? Now, I'm gonna let you guys do this stuff. I just wanna get you, kind of steer you slightly in the right direction before you tackle this assignment.
Alright.
Okay, good. Okay, this one, I didn't mean to put this problem on there, but being as it's on there, I'll just show it to you real quick. Really simple.
Oh.
All orders of the function. So we can do higher order derivatives, and that sounds really impressive, but it's no big deal. Here, let's do this one together, 'cause it's so easy.
Oh, yeah.
So what's y prime?
1/8 x to the third.
Oh, what am I gonna get from that first term? X cubed, right? Good. So I'll get x to the fourth over 4.
Yeah.
Dividing by 4 is the same as multiplying by 1/4, right?
Yeah.
So I'm gonna get an x cubed plus, what, 24/9 x squared
Yeah.
minus 2x
Yeah.
plus 5,
Mhm.
okay? What if I were to take a second derivative? All that is, and we'll talk more about what these mean, later, but for now, just in terms of actually executing the calculus, the second derivative is just a derivative of the first derivative. So we could go on, I don't write it that way, write it like this, sorry. X prime, y prime prime, or f double prime of x.
So you just keep going with the prime.
Yeah, I just
3, 4.
exactly, so I'd just become a 3x squared, right? See what I'm doing?
Yeah.
Plus, et cetera, and then if I did y triple prime,
Yeah, I'm seeing
that's
it.
just gonna be
6x.
God.
6x plus, see what I'm saying?
Yeah.
Jeez.
I gotcha.
Okay?
You're breaking it down.
Dude, I'm seeing it.
Okay, now we get into something,
Swaggle.
now this is near and dear to my heart, now we're talking about some physics, and I like this.
Oh,
Mm.
no, thank you.
Oh, no, this is the greatest.
I'm a
Okay,
genius.
so what I need to tell you about this, and some of you guys, how many people are in physics? Okay, good, and have you started talking about kinematics, obviously? Yeah, so this is gonna be old news to you, and you can provide some expertise here. I'm gonna be presenting at a conference on Monday, and so I won't be at school, so you guys have gotta be just working. You people that have a little physics understanding and background, you can share the wealth with these other yahoos.
I'm too young. Sorry.
So-
nothing I can do.
So here's what you need to know though, in a nutshell. And we're gonna do a lot with this. This kinematics is a great vehicle for exploring calculus. So if this is what we call position, right? Our position function is, usually we write it as s in physics, could be x, but this is s, and I really should write it as s of t. It's a function of time. It's one, in this case, 1 minus cosine, 3 cosine t. Whoops. So what that's telling me then is the position, and presumably this is just on a line. In fact, this is a simple harmonic motion. So it's something like, the picture we would draw that maybe this represents is like, here's a wall, there's a spring, and there's some weight attached to the spring, and we like compress it and let it just go back and forth like that. So it's something like that.
That's cool.
Okay, it's because cosine is we know what cosine just looks like a wave train. And so this is just kind of wavering, the position's just changing positively and negatively and positively and negatively. And we'll spend more time talking about this stuff later, it's really interesting. But for now, this is all you need to get started. So if this is the position function that predicts the position as a function of time, and if I were to graph that, in this case, it just looks something like this. Right, if this is my position, maybe distance away from the wall, and this is time. Does that make sense? I just can't go through the wall, but I don't need distance away from some mark on the ground or something like that. If this is position, then velocity is defined as, and we know what velocity is, right? Velocity is just speed with direction associated with it. So whereas speed is what you read on a speedometer, velocity would be like, let's say that direction's positive, this would be considered positive velocity, whereas this would be considered negative velocity because I'm going backwards.
Yeah.
And we'll talk more about that too, but that's again, for now, that's probably good enough. And I'll give you a few days on this assignment. I want to make sure I'm here to answer questions when I get back.
Oh, yeah.
So V of t is just going to be ds dt, or a better way of writing it, s prime of t. Velocity is just the derivative of position with respect to time. How about that? Okay, that's velocity. And acceleration is what? Derivative of velocity, exactly. Okay. So another way of writing acceleration would be
The following students are needed to form
the second derivative of position. How about that?
Schiller, Christina Thompson,
Now, there's a weird
Trevor
question.
Sweet, Tyler
So,
Lenny,
you're not gonna get
and
all
Michael
this today,
Swanson.
but this will get you
Please
going
go
on it.
forward.
You can spend some time on this over the weekend. What about this one? This is a weird one. You almost never see this in physics. Find the jerk at time t. Some physicists had a real sense of humor about this.
God, what is going on?
The jerk is the derivative of acceleration with respect to time. And it's pretty obscure. You can't, we don't talk about it very much because it doesn't have a lot of physical meaning. You can't really relate well to a jerk. Maybe that's why they called it a jerk, I don't know. But, so it'd be the derivative of a with respect to t. So it's really no big deal, it just sounds weird. Okay, what about this? Find the equations for the lines that are tangent. We can do that, right? Tangent line, we'll find the derivative. That's gonna give us m, that's gonna give us the slope.
Yeah.
We'll substitute and we'll find the point of tangency like we talked about, and there's our
I can do
point.
that.
No big deal, but what does this word mean? Find the tangent, lines that are tangent and normal to the graph. Normal's another big time word in math and calculus. Normal just means perpendicular.
Yeah.
It's perpendicular. So if this is my curve, and this is a point of tangency, so there's the tangent line, then this is gonna be the normal line.
Yeah.
Okay?
Uh-huh.
And that's a big word in calculus. As you guys do more calculus, you're not doing calculus-based physics. I mean, if you do more physics. You're not doing calculus-based physics, so you're not gonna probably talk about all these terms as much, but when you start doing things like, friction, talk about kinetic and static friction and things. Well, one of the ways, you have to talk about the normal force. How hard is an object being pushed into a surface, and that contributes obviously to the amount of friction it experiences. All right, so this might be where we're getting pretty close to the end, aren't we? Yeah, we'll get to it. Okay, so here's another great way that calculus it just takes what you know and just makes it so much better. Write the circumference of a circle as a function of the radius. Well, that's no big deal. We'll do this one together. So circumference would equal what? 2 pi r. Yeah. And so let's say that this circle is variable. Let's say the circle can shrink and grow, right? If the circle can shrink and grow, then we could also say C of r, because circumference is really a function of the variable r, isn't it? Would equal 2 pi r. And just using this function notation just reminds us which is the independent quantity and which is the dependent quantity here, right? Okay, so it wants us to find the instantaneous rate of change of circumference with respect to radius. Now that's a big topic. That's really cool. What that's saying is, as this circle morphs from small to big, or big to small, how fast is the circumference changing with respect to or compared to the change in the radius? Okay, that's a really valuable thing to know. A lot of times that's important to know in life. We want to know about these things, rates of changes. We want to know, sometimes absolute quantities aren't that important. If I said that, what's an example? Would you rather have, let's say you're going to have a mutual fund for 30 years. Would you rather have one that's presently worth $100,000 and growing at a rate of 1% per year, or one that's presently worth $10,000 and growing at a rate of 8% per year? You're going to want the second one, I guarantee it. So in this case, it's the rate of change of the principal that's far and away the most important quantity, right? And so if we want to find this then, in calculus, that's a derivative. That's really what a derivative is. A slope, in the past, you've always equated with the rate of change. Well, a derivative is an instantaneous rate of change, right? And so if we talk about something like c prime of r, and in this case, we might actually write it as dc dr, because it's telling us the rate of change of circumference with respect to radius. Right? It looks more like a slope than rise over run. And if we were to graph this thing, it would just go something like this, wouldn't it? If that's circumference and that's radius, it's a linear relationship. See what I'm saying?
Yes.
And so that's why this is kind of a neat way of saying it, because really we're just looking at the slope of this line at any point. But what's that going to be if I differentiate this with respect to r? That's a little strange. In the past, we've always used like x's and y's or x's and f's, but all it is just changing variables. The same process exactly applies that we've been talking about. And so what is this derivative? What is dc dr, or c prime of r? If r is the variable. That's just like saying r to the 1. What's that going to be? What if those were x's? What's the derivative of 2x? Just 2, right? Yeah. So what's the derivative of 2 pi x? 2 pi. What's the derivative of 2 pi r with respect to r? 2 pi. That's it. Okay, that's it. Right, and so if we want to know what's the rate of change of circumference when r equals 1? 2 pi. There's no r in our answer, right? When r is 5, it's 2 pi. Now, if we had done something different, if we had maybe found the rate of change of area is pi r squared, right? And so now dA dr, or a prime of r, same thing, would equal what? That's an r. Okay, that equals 2 pi. Isn't that interesting?
Yeah.
Circumference?
Yeah.
Isn't that pretty cool when you start to see these things?
That's very.
Okay. So this is going to change, isn't it? For different values of r, the rate of change of area is going to increase. That makes sense too, and we'll talk some about that. I mean, if you look at if we were to graph the function a versus r, pi r squared, isn't that going to look something like that?
Probably.
It's parabolic, right? It's r squared. It's quadratic. And so you can see that this slope of the tangent line is increasing as r increases. That's what the derivative is telling us, right? Isn't that cool? That's pretty good stuff. Okay, so now this is great. This is good. Oh, this is like a puzzle. You're gonna love this. This is fun.
Oh, yes.
An object thrown vertically upward from the surface of a celestial body at a velocity of 15 meters per second reaches a height of s equals 15t minus 0.3 t squared meters in t seconds. So what that's giving us the position function. The height is a function of time, right? Write that again. S of t equals 15t minus 0.3 t squared. So if we want to do something like find the object's velocity and acceleration as functions of time, I'm just going to take a first derivative and second derivative, right? No big deal. How long does it take the object to reach its highest point? Now, that's a cool question. to reach its highest point, what's gonna be one of the distinguishing characteristics of that highest point, the apex of its trajectory? When it's up here, what's one thing that happens? What's it again? Velocity zero, yeah. So if we wanna find how long it takes to get there, we could set the velocity function equal to zero, right? And solve for t. And that's like asking the math gods, when is it come to its highest point, right? Because we know that when the velocity is zero, it's at its highest point. Isn't that, so you can figure out very precisely when it's gonna be there using calculus. Okay, what about, how high does the object go? Well, we might use the answer to part B. To part C, we already know the time at which it's at its highest point, right? That's when the velocity was zero. How could I use that information to find out how high it actually goes? Plug it into, yeah, the position function. Yeah, you see what I'm getting at? So I don't want to spoil all the fun. I'll let you guys figure out the rest from there. But you can use these kinematics to solve lots of real world questions about a situation, right? Let's see, one more. No, it's not. That's it. Okay. Oh, look at that timing. You lost.